Hello, everybody. I'm Masafumi Hashimoto, Dosha University, Japan. I'll talk about simultaneous localization, mapping, and moving object tracking using helmet-mounted LiDAR for micromobility. This shows a brief history of myself. This shows the agenda of my talk. I begin with the motivation of our research. Environmental map building using simultaneous localization and mapping SLAM and the tracking of moving object TMO are important issues for autonomous driving and active safety of vehicles and mobile robots. So many related studies have been presented using cameras, radars, and LiDAR sensors. Today, we focus on LiDAR-based SLAM TMO. Due to the impact of COVID-19, many people are highly resistant to using conventional means of urban transportation. To escape the three C's, the use of single-seater micromobility, such as bicycle, e-bike, e-scooter, and personal mobility, is on the increase for short-distance travel in urban cities. In the endemic society, the demand for micromobility will further increase. Although the frequency of traffic accidents involving micromobility increases, the R&D related to active safety for micromobility is far behind. So, in my topic today, for active safety of micromobility, SLAM TMO method is presented in GNSS denied environment using a LiDAR attached to the rider's helmet. We say helmet-mounted LiDAR of micromobility. And this shows the overview of our experimental system. A LiDAR and IMU sensors are set at the top of the helmet. These are the specifications of these sensors. This shows the sequence of our SLAM TMO. Blue parts is the SLAM module and the pink part is TMO module. LiDAR obtained the scan data, but this LiDAR scan data has a distortion. Distortion in the LiDAR scan data, which is caused by motion of micromobility and LiDAR is corrected. After that, the self-pose of the helmet is obtained using the normal distributions transform NDT scan matching. And we classify the scan data into the stationary scan data relating to stationary objects and moving scan data relating to moving object. Stationary scan data are applied SLAM environment map building, and moving scan data are applied to moving object tracking, TMO. I explained the SLAM briefly. SLAM has two different scans. One in the reference scan obtains before the current scan, which is represented as a world coordinate frame. Another is the new scan data obtained at the current scan, which is represented in the helmet coordinate frame. The helmet LiDAR obtains the new scan data every LiDAR scan period. And using the NDT scan matching, the helmet pose, 3D positions, and the roll pitch and yaw angles is calculated by matching the new scan data with the environmental map. The new scan data are merged to environment map using the calculated helmet pose. By repeating this process every LiDAR scan period, the environment map can be built. Next, I explain the distortion correction of LiDAR scan data briefly. We usually assume that all LiDAR scan data within the scan, one rotation of laser beams in the horizontal plane are obtained at the same time. Thus, all scan data are mapped onto the world coordinate frame using the same posable LiDAR. However, the LiDAR obtains measurement by scanning laser beam like this. Thus, when the helmet moves, shakes strongly like this, all LiDAR scan data within a scan cannot be obtained at the same pose of the LiDAR, and the distortion appears in mapping result. This shows the example of LiDAR scan data distortion. A LiDAR obtains the image of a tree, and then the distortion appears. To correct such distortion, the helmet pose is estimated using a Kalman filter-based method. Every LiDAR scan data are obtained within a scan. Then we can correct the distortion like this. Next, I explain the classification of LiDAR scan data briefly. For SLAM, the scan data related to a stationary object have to be extracted from the entire LiDAR scan data. On the other side, for TMO, the scan data related to moving object have to be extracted from the entire scan data. Although the usual classification of LiDAR scan data is performed based on the occupancy grid method, LiDAR noises and outliers frequently cause misclassification. To classify the scan data as much correctly as possible from LiDAR scan data, we present environment map subtraction-based classification method. This shows the overview of EMS-based classification method. This is the environmental map obtained by NDT-SLAM, and this is the current scan data obtained every LiDAR scan period. The environment map is subtracted from this current scan data, and then we can obtain such extracted scan data. Based on the occupancy grid method, stationary and moving scan data are classified from these extracted scan data. Now, I explain the occupancy grid method briefly. LiDAR scan data are extracted based on the EMS-based classification method just mentioned. Extracted scan data are mapped onto the elevation map, which is represented in the world coordinate frame. For the stationary scan data, the time to occupy the same cell is long. On the other side, for the moving scan data, the time to occupy the same cell is short. So, based on the occupancy time, stationary moving scan data can be classified. Next, I explain the moving object tracking, TMO, briefly. In TMO, first of all, I obtain the width and the length of moving object from the moving scan data. After that, I estimate the size of moving object by this equation, width and the length. The height estimate of moving object is directly obtained from the height measurements of moving scan data. And I obtain the position of this geometric center of estimated cuboid. Based on the position of geometric center, I estimate the position and the velocity of moving object by a Kalman filter. Next, I'll show you some experimental result. I moved a micromobility on our university campus road from here to here. The travel distance of the micromobility is 500 meters and the maximum speed is 30 kilometer an hour. This shows an example of TMO result. A micromobility is here. The micromobility tracked two pedestrians and a bus. Rectangle angles are the tracked object, length and width. This bar is the moving direction of the velocities. I examine the performance of moving object tracking. In the environment, the number of moving objects is 111. I conducted the experiment in two cases. Case 1 is a SLAM MTO with distortion correction of LiDAR scan data and EMS-based classification method. This is our proposed method. Case 2 is SLAM MTO without using either method. This table shows the result, number of moving objects tracked. Case 1 is here and case 2 is here. From this table, our proposed method, case 1, gives better moving object tracking accuracy. This shows an example of SLAM, environmental map building. This shows the overall map, and this shows the enlarged map in this area. I examined the performance of SLAM. In the SLAM, the mapping accuracy can be evaluated by the pose accuracy. So I obtained the error of position estimate at the helmet at the goal position. I conducted the experiment in two cases. Case 1, SLAM MTO with the distortion correction of LiDAR scan data and EMS-based classification method. Case 2 is the SLAM MTO without using either method. This showed the error of position estimate at the goal position. We conducted 3 rounds. From this table, the proposed method here gives a better SLAM accuracy. Conclusions. I presented a SLAM MTO using helmet-mounted LiDAR, and I corrected the distortion of scanning LiDAR data. Also, I classified the stationary and moving scan data, and finally, I examined the performance of our SLAM MTO. As a future work, I will detect obstacles on road surfaces to reduce the falling risk of micromobility, and I will include the obstacle information in the environment map. Secondly, since the current helmet-mounted mechanical LiDAR is heavy and large, there are issues in terms of practicality and usability. Therefore, instead of mechanical LiDAR, I will mount the small size and lightweight solid-state LiDAR on a LiDAR helmet. That's all. Thank you for your attention.